In this collection of videos, we are going to provide the definition of the abstract algebra concept of a group, and we're going to work through a lot of common and uncommon examples of groups as a preliminary introduction to the subject. So let's start with the definitions, and before we get to the definition of what a group is, we need to discuss what a binary operation is. So let's start with that definition. Let's suppose that G is a set, any old sets. Then a binary operation, which we're going to denote with a dot on the set G, is a map or a function. The domain of this function is this Cartesian product of this set with itself, which we denote by G cross G. And the range of this function is the set G itself. So this Cartesian product can look a little bit annoying. I mean, the most common place you've seen this is sort of when you're talking about the plane and you're representing things as ordered pairs, where the first element is a coordinate of G, and it's an ordered pair A comma B. Both elements A and B come from G. This is the formal definition of a binary operation. It's a map from G cross G to G. A better way of thinking about what a binary operation is that it's a method of taking two elements of the set G and combining them somehow into a single element of the set G. That's probably a better way to think about a binary operation, but this is the formal definition for us. Now, if you want to speak more about the set than about the operation, as we often will, another common way to talk about a binary operation is to say that the set G is closed. So if you have a particular set G, and it happens to be the case that the map dot that you have is a binary operation, another way of saying that dot is a binary operation on the set G is just saying that G is closed under the operation dot. And sometimes you'll even hear people say things redundantly, saying this binary operation, this set is closed under this binary operation. And then they're saying, kind of both at once. Now let's give some examples of operations that are binary operations on particular sets. And both are important in this. So one common binary operation that we have is addition. Right? So what do we mean? And addition is a binary operation on the set of integers, the set of rational numbers, the set of real numbers, and the set of complex numbers. So what this means is that if I take two integers and I add them together, if Z is my set, if I take two integers, I add them together, I get a single integer as the output, and it happens to be the case that that's an integer. I don't take two integers and add them together and all of a sudden get something that's purely a complex number. Similarly, if I take two fractions and I add them together, I get another fraction. I don't get something that's purely complex or purely imaginary or irrational, nothing like that. The sum of two real numbers is a real number, and the sum of two complex numbers is a complex number. So each of these sets individually is what is called closed under the operation of addition. A less common example of a binary operation, but an example that we've seen is we've worked the example of kind of the motions of a square. If you have two different motions of a square that will move the square without knowing you've moved it. So for example, if you take a square and you rotate it by 180 degrees, the resulting thing is still going to look like a square. And similarly, if you take a square and you flip it across the vertical axis of symmetry of that square, it's still going to look like a square. And the binary operation of kind of concatenating those two motions, almost like a function composition, or just combining those two motions at once, will give you another set of symmetries of the square. So, for example, if I first take a square and rotate it by 180 degrees and then flip it across a vertical axis of symmetry, I still have something that looks like a square after combining those two things together. Another, perhaps less common example of a binary operation is if I take G to be the real numbers and then I look at the map bullet that takes R cross R to R by projecting onto the first coordinate, then this is a binary operation as well. And a non-example is always helpful in order to illuminate what this operation is, what this definition is not. For example, something that's going to be important to us in group theory is that division is not a binary operation on the integers. So if I take two integers, if division is my operation and I take two integers a and b and I want to combine them by taking A and dividing it by B, it is no longer the case that the output, A over B, is necessarily an integer. It could be if I picked integers like 6 and 3, and I took 6 and divided it by 3, I'm going to get 2, which is an integer, but it need not be. If I take 7 and 3, for instance, I take 7 divided by 3, I get a rational number, but not an integer. So what I'd be violating is, in terms of this very formal definition, the output, 7/3 of division by taking a 7 and a 3 and combining them, is a rational number, not an integer, and so I'd be stepping outside the range, the required range according to this definition. I would need the range to be the integers, and it isn't necessarily. Now that we have the definition of a binary operation, we can go on and get to our formal definition of a group. So let's suppose that G is a non-empty set. Then we will say that G is a group as long as it satisfies 4 particular properties. So the first thing is that this set needs to come along with a binary operation. And so what we say here is that G is closed under a binary operation dot. So it has to be the case that you have a binary operation on the group, and that has its own requirement. You have to check that this operation that's been given to you along with the set really and truly has the set is closed under that operation. The second requirement, which is most often the most technical, I guess, and the most annoying criteria to satisfy, is that this operation that you've been given along with your set needs to be an associative operation, which means that whenever you take 3 elements in your set, which we'll call A, B, and C, and no matter what those 3 elements are, if you first use your binary operation to combine A with B, and you get an output, which is a single element of G, and then you take that single element of G and combine it under your binary operation with C, this has to be the same thing as if you would have first combined the elements B and C under your binary operation, and then combine the elements A and A with, that output, in that order, reading left to right. So you have to be able to shift your parentheses in this particular way. So sometimes people get confused about what's the difference between something that's associative and something that's commutative, and something that's commutative we'll talk about later. But in commutativity, you have a statement of equality where you're changing where the elements are. When you're talking about the statement of associativity, you're changing where the parentheses are. So notice that on both sides of this equation, I have A, B, and C written in exactly the same order. A comes first, then B, then C. All I've done to go from the left to the right is I've changed where the parentheses are in this statement. When we see the statement of what is called a commutative operation, we'll see that this does not involve parentheses at all. It involves moving around the order of the letters. So associativity relates to moving the order of the parentheses. Commutativity is going to relate to moving the order of the letters. Back to our definition of a group, there's our third requirement, and this is a very nice requirement. It says there exists an element that we're going to denote by E, which is called the identity of the group G. And what does this identity do? Hopefully this will become intuitive to you as we work through some examples, but the statement of the identity property is that whenever you take any old element in the group, if you combine this arbitrary element A for arbitrary, with this identity element E, in either order, either the ordered pair A, E, or the ordered pair E, A, when you combine them together using this binary operation, no matter what order you do this in, you always get as your output the same thing that you plugged in against the identity. So A dot E is equal to E dot A is equal to A itself. Again, this should seem intuitive to you once we see some common examples of groups. And the very last requirement that we have, the fourth and final requirement to be a group, is that for every element, for each element A and G, there exists a special element associated with this A, which we're going to denote by A inverse. And this is called the inverse of A. And what does this inverse have to do? Well, it relates to the identity, this special element that we've called the identity from the previous requirement, which is if I take this element A and combine it under my binary operation with the inverse, that this is in either order, so that's the first equality here, that I want the output now to be the identity. So take an element, combine it with its inverse in any order, and I want to get back to this special element that we've called the identity of the group. So these four things are the requirements that need to be satisfied in order to be a group. So as we'll see as we work through some examples later, if somebody says, prove or disprove that this set along with this operation form a group, if you're proving that that does indeed form a group, you need to go through these properties, these four things, and just show that they're each satisfied one at a time, and then you'll have proven that something forms a group. What I do want to make clear, which is a really common mistake for people in an abstract algebra, is now is where I want to come back and talk about commutativity. We do not require that the operation, this binary operation coming along with this group, be a commutative operation. That is, we do not require that A dot B equal B dot A for all AB in the group. It may be the case that that's true, but we don't require it. It's not necessary in order to be considered a group. Now, in my class I have, before starting this material, I have you work out the set of symmetries of a square to kind of see that this forms a group, and you notice that the order in which you combined things, the combined motions of the square, is important. Meaning, for instance, that if I first rotate the square by 90 degrees and then I flip it along a vertical axis of symmetry, if I did that in the other order, I'd get a different answer. What that is saying is that if I first do motion A and then combine it with motion B, or if I first do motion B and then combine it with motion A, I can get two different answers. And that's okay. I still have something that's a group. It violates this property right here, the order in which I do things. I don't have equality here, but I still get something that forms a group. And it's very, very important to realize that this is not required. And when you're working your proofs, it's very important for you not to use that an operation is commutative unless you know that for sure, because it's not built into the definition of a group. Now, if a group does in fact satisfy this property, that is, no matter what two elements you pick in the group, it always turns out that A dot B is B dot A, then what you can say is one of two things. You can either say that the operation dot is a commutative operation, or you can say that the group G, the set G, is an abelian group. This is more often the notation that I use. I more often use the word that corresponds to the set to say that the group is an abelian group. I say that more frequently than saying that the operation is commutative. Before ending this first introductory video, I do want to go back and I want to cover the most familiar examples of groups to hopefully make the definition of a group seem more intuitive. So our most familiar examples of groups are our very familiar number systems, like the integers, the rational numbers, the real numbers, and then maybe the complex numbers. All of these things are groups under the operation of addition. So let's talk about this a little bit. First of all, we discussed when we discussed binary operations that each of these sets, it is indeed true that each of these sets is closed under the operation of addition, meaning if I take two integers and I add them together, I get another integer. So each of them is closed under the operation, and that is the first requirement of a group. We need to have closure. The next requirement that we have is we need the operation of addition to be associative, and this is a fact that we are quite familiar with from growing up and learning about number systems. It is true that the addition operation is associative. You are at will to move the parentheses around when performing a computation of straight addition in regular arithmetic. The next thing that we need is an identity. So the next requirement of a group is that there has to be a special element called the identity of the group, for which whenever I take any old element of the set and I combine it under this operation in either order, then I'm going to get the original element that I started with. And for each of these number systems, the integers, rational numbers, reals, and complex, that identity is the number 0. When I take any old number in the world, say, be it -5 or 7/3 or I or pi, if I add 0 to that, it doesn't matter what it was, I get whatever I put in right back. So negative 5 plus 0 is negative 5, 7/3 plus 0 is 7/3, I plus 0 is I, and pi plus 0 is pi. So that's our special element, that's the identity element. When I add 0 to something, it has the effect of doing nothing. And last but not least, every element of your set needs to have an inverse under this operation. So if I take an element, for example, let's use 5 in the integers, I need to be able to find an integer so that when I add it to 5, I end up at the special element, which is the identity. Now we've discussed that the special element is 0, so if I take 5, I'm looking for some number that I can add to 5, and I can get back to 0, and that special number happens to be negative 5. And sure enough, negative 5 belongs to the integers. So I do have an inverse of every old number. It's the number that we commonly refer to as sort of the negative of that number. So I would call it the additive inverse. So the additive inverse of 5 is negative 5. 5 plus negative 5 is 0. So, proof by example, the integers, the rational numbers, the real numbers, and the complex numbers are all groups under addition. In a very similar manner, if I start out with a particular modulus n, so a modulus is any old integer that isn't 0, and if I look at the integers modulo n, then these form a group under what I have in parentheses here is modular addition. So let's think about the integers modulo n. Let's think about n as our modulus. We'll think about the integers modulo n as the set of numbers 0 up through n, the set of integers 0 up through n minus 1. So the numbers less than n, but greater than or equal to 0, the integers with that property. That set of integers will form a group under what I'm going to say modular addition. So for instance, if I take my integers, if I pick my number n to be 3, and I take 1 and so my set that would be forming a group here is the set of numbers 0, 1, 2, all of the numbers greater than or equal to 0 but less than 3, all of the integers with that property. If I add them together, if I take 1 plus 2, I'm going to get 3, and 3 is too big. It's not in my original set 0, 1, 2. But what I'll do is I'll take 3 and I'll read it modulo 3. So I'll associate 3 with its remainder when I divide by 3, and its remainder when I divide by 3 is 0. So when I take something like 1 plus 2 and I add them together, instead of saying the answer is 3, I'll say that the answer is 3 mod 3, which is 0. And so if I'm using modular addition instead of regular addition, then it happens to be the case that the integers mod n will form a group under this operation. And it doesn't matter, n is 3 was my example, but any old n that isn't 0 will work. I guess if I'm defining the integers mod n in this way, then I should say any old positive integer will work. Now, the next example that I'd like to do is a non-example. The integers are not a group under multiplication. Now it is true that if I take any old integers in the world and I combine them via multiplication, then I get another integer. So the integers are closed under multiplication, so that's not a problem. Multiplication is an associative operation, so I don't have any problems with associativity. I even have a multiplicative identity that happens to be an integer. That is, I'm looking for a number. If I'm looking for a multiplicative identity, I'm looking for a number so that when I take any old integer in the world and I combine it under the operation of multiplication with this special number, I want to get myself back. So the answer for that is if I take any old number in the world, like 5, and I multiply it by 1, then I'm still going to get 5. Multiplying by 1 doesn't change anything. And that's true of all integers. Any old integer in the world multiplied by 1 is itself, and so the integers do have a multiplicative identity. So I've claimed that the integers are not a group under multiplication, but they satisfy the first 3 properties of being a group. What they fail is to have inverses. So now that I know that 1 is going to be my multiplicative identity here, what I would have to do in order to be closed under taking inverses, or in order for every element of my set to have an inverse, is I'd need to answer the question. If I start with an integer, let's take 2 for example, I'd be looking for another integer to multiply 2 by in order to get this special identity, which is 1. So I'd be trying to solve the equation 2x is equal to 1. There's a solution to that. It's x is equal to 1/2. However, 1/2 is not an integer. So there's no integer in the world that I can take and multiply by 2 to get the number 1. And so this means that the set of integers fails to possess multiplicative inverses. So the integers do not form a group under multiplication, and the reason for that is the integers fail to contain multiplicative inverses for all of their elements. Now, if you move away from the integers, it's not that multiplication is a fundamentally bad operation, it's that the integers aren't really large enough, so to speak. In order to find ourselves with closure under taking inverses, right? So we saw that there's a problem with the integers. It's that something like 2 doesn't have a multiplicative inverse. It would need to contain 1/2, and it doesn't. If you go up from the integers to the set of all fractions, then you're not going to have any problems anymore. If I take a number like 2, I'd be looking for 1/2 in order to be its multiplicative inverse. 1/2, although not an integer, is certainly a rational number. And so the rational numbers are big enough to possess the inverses of all their elements. Right? That is, if I take a fraction and I'm looking for its multiplicative inverse, it's the reciprocal of that fraction, which is another fraction. And so I'm going to be fine in terms of the rational numbers, the real numbers, and the complex numbers. Each one of those sets is large enough to satisfy this multiplicative inverse property. All the other properties are fine, as we saw in the previous example. And so the rationals, the real numbers, and the complex numbers are almost groups under multiplication. The problem is we need to remove 0. So if we're willing to part with the number 0, then the rational numbers, the real numbers, and the complex numbers will be groups under the operation of multiplication. This is because 0 does not have a multiplicative inverse. If I'm looking for a solution of 0 times x is equal to 1, there are no solutions to that equation in the rationals, the reals, and the complex numbers. And so, since we're not allowed to divide by 0 to solve for x, and so 0 is going to cause us a problem. Any other number in the world we're allowed to divide by, so we'll be able to solve that kind of equation, ax is equal to 1, within these number systems. So as long as you get rid of the number 0, the rational numbers, the real numbers, and the complex numbers do form groups under the operation of multiplication. The last of our familiar examples of groups, before we'll stop here, is I'm going to include the set of symmetries of a square inside familiar examples of groups, since I've done this as an activity with my classes. This is something that they've seen before, so this is moving out of the realm of things that are extremely normal. But let's talk a little bit about, we've talked about what the binary operation is. It's the combination of these motions. We've discussed that this is not an abelian group, the set of symmetries of a square. It does turn out that the operation is associative. That is the hardest thing to prove. But looking at a Cayley table is really enough to give you the rest of the properties. So the fact, when you complete a Cayley table on the set of symmetries of a square, you see that no matter how you combine any two things, anytime you go to any particular row in any particular column and you look at the entry that lies inside the Cayley table there, you find another motion of the square. And so the fact that you don't find something outside of your list inside your Cayley table tells you that you have closure of your operation of combining motions. The fact that you could find what I was calling R sub 0, which is don't do anything to the square, very silly symmetry of the square, but a symmetry nonetheless, that's going to be your identity. If you first don't do anything to the square and then do another motion, that's the same as just doing that motion. So that's going to be your identity, and the fact that you see that entry, that R sub 0, appear in every row and column inside your Cayley table is enough to tell you that every motion of the square has an inverse. This is something that's fairly intuitive. If you take a square and you rotate it by 90 degrees clockwise, you can undo that motion by rotating by 90 degrees counterclockwise. And so this is something that's that should be intuitive and line up with the example that my classes worked.